And today I will introduce our work, Render-Based Factorization for Additive Live Field Display. This work is completed in cooperation with Zhenyi from New York University and Xubo from Shanghai Jiaotong University. Great thanks for their excellent work. Display play critical roles in AR and VR systems. Traditional displays involved in such systems include LCD screens or projectors, which are generally monoscopic. HMD is another type of AR/VR display, which has gained more and more attention in recent years. Although it can provide stereoscopic views, viewers still suffer from visual discomfort caused by vergence accommodation conflict. When viewing in HMD, the viewer can receive depth information of a virtual object through the vergence of stereoscopic image, shown as virtual distance here. However, no matter how far a virtual object is, it has to be rendered on the display plane, which has a fixed distance from the viewer. This results in a fixed accommodation distance. In brief, the vergence distance and the accommodation distance are generally different in HMD, which is a key factor for visual discomfort. To solve this problem, many kinds of displays were proposed in the last several decades, such as volumetric displays, holographic displays, and live field displays. Live field displays aim at reconstructing a target live field to give the viewer a correct focus cue. According to the reconstructing principle, live field displays can be further classified into micro-lens array, multiplex, and additive live field displays. The multiplex and additive live field displays are both using multi-layer structure. The difference is the way how to combine the layers. The layers in multiplex design are constructed to attenuate the passing light, while the layers are constructed to add light in the additive design. In our work, we focus on the additive live field display. The additive live field display has several benefits compared to other types of accommodative display. First, it can be applied to AR applications easily. Second, it can be implemented in a lightweight and compact form. Third, it is relatively free from brightness and diffraction problems. There are also problems with additive live field display. The challenge is that the live field factorization approach is computationally expensive. It's not adequate, especially for AR/VR applications, which require high frame rates, generally 50 FPS or more. Our work accelerates the factorization approach so that it can be run in real time now. Let's take a look at the general approach before moving on to our approach. Following Levoid and Heinrich's work in 1996, the live field is represented as a 4D function LXU, where X and U are 2T coordinates on two parallel planes in the space. Let's define one plane as the view plane, where the I is X. Another plane is 1 unit away from the view plane. For an additive live field display, several transparent display layers are placed at different distances from the view plane, defined as D1 to Dn. The constructed live field can be calculated using the formula. It's the sum of all layers with a simple coordinate transform. Given a live field as target, the ground truth, what shall be shown on this display layer? This problem can be described using an optimization equation. After calculating the reconstructed live field, an L2 distance can be measured between itself and the ground truth. This defines the loss function to be minimized. An additional constraint should be considered because display layers have fixed brightness range. Let's say between 0 and 1. To solve it by computer, Li et al. And Zhang et al. discretized the problem into a matrix-based form. Here comes with a simple example. There exist two display layers, and the discretized light field has only two viewpoints. They built a mapping matrix P between the vectorized form of the light field and the display layers. Each row in the matrix P corresponds to a light ray of the light field. With this representation, the optimization equation can be turned into a bounded linear square equation. It can be solved using trust region algorithm. However, it's slow. It costs several minutes to solve a frame. In this work, we propose a render-based factorization, accelerating the factorization process by using GPU's render pipeline. At the start point of the application, two sets of mapping textures are built using rendering approach. P are the mappings from light field space to screen space, and the Q are the mappings from screen space to light field space. Now, for the target light field L0, we constructed light field LR in light field space and the set of display image II in screen space. We do the following process. First, map two light fields to screen space using P. Second, update display image by difference of two mapped light fields. Third, map display images reversely to light field space and update the reconstructed light field. These three steps are looped for several iterations in a frame. The mapping operations are done by general texture working process. The layers update step updates display layers using this formula. All steps are implemented on GPU using render pipeline, so the iteration can reach high performance. We further optimize the process by proposing the depth-aware initialization strategy. General, solid, or random color are used as initial condition. From the result of factorization, we found the assignment of colors on layers highly depends on the depth of the object. So we designed a depth-aware initialization strategy. A rendered scene and its corresponding depth buffer are used as input. Colors of the rendered scene are assigned to a layer with a weight alpha calculated by the formula. Here we choose an example. For objects before or on the first layer, we assign them to the first layer only. For objects after or on the second layer, we assign them to the second layer only. For objects between two layers, we assign them to two layers according to the distances. Now let's see the result. The experiments are done on this computer. It's built via Unity run on Windows 10 as the render engine. We simulated a two-layer adaptive light field display. Each layer has 1,280 times 960 pixels. Two layers are put at 1.4 and 2.1 meters from the viewer. We discretized the light field to 1,280 times 960 views. These 9 views are uniformly sampled in a 0.1 meter square region. In the study, we built 3 test scenes. The first is called primitive, which contains 3 primitive models. The second, called Stanford, contains 3 models selected from the Stanford 3D scanning repository. The third, called village, is a cartoon-style village scene. Here we show the study results. To begin with, here lists the performance compared with MATLAB and the MGPU. MGPU means the GPU accelerated matrix-based approach. Last 2 columns are our performance. Our approach gains 160,000 speedup compared to MATLAB and 7 times speedup compared to MCPU. The performance of our method satisfies the performance requirement for real-time application. Now let's see the quality of our approach. The differences between our reconstructed light fields and the tapped light fields are difficult to catch by eyes except around the boundaries of objects where unremarkable Gauss effects exist. Here is another thing, the Stanford. And the village scene. Another artifact in scene village is the blurry background, which exists both in our method and in MATLAB. It indicates that additive light field factorization has a limitation on handling objects beyond the range of distance covered by layers. We then evaluated quantitatively using peak signal to noise ratio and plotter bar graph. Our method reaches competitive quality compared to the matrix-based factorization method. We also noticed that our methods perform poor in village. It is probably because the background objects are positioned out of the layers range, as I mentioned in the last slide. To show the effectiveness of the depth-aware initialization strategy, we compared the convergence between the depth-aware initialization strategy called DA and the solid color initialization strategy called SD. The colored lines in the plot are the root mean square errors of these two strategies related to iterations. DA leads to significantly lower error and faster convergence than SD. These three patches show detailed differences of reconstructed light fields between the two strategies. In general, DA results in overall better quality, although some degradation exists around the hard edges of objects. See the yellow dashed squares. We do a fixed number of iterations for each frame. So how to choose this number? It's a balance between quality and performance. Thus, we propose to use joint error, which is defined as a combination of quality error and performance error to describe it. We use the root mean square error as a quality error. The performance error is defined as the square of time divides TS, a soft time threshold value, which means time below the value is an acceptable performance. We set TS to be 30 milliseconds in our evaluation. Alpha is the weight of the performance error, which is set to 0.01. The optimal number is the number minimized the joint error. We plot our evaluation results and show that the optimal numbers for depth-aware and solid color are 5 and 8 respectively. That means 5 iterations per frame achieves a good balance between quality and performance for depth-aware and saves about 40% iteration compared to solid color. Below is our contribution. We propose a render-based factorization for additive light field displays, achieving real-time performance and high quality. We optimize the initial condition of factorization using the depth-aware initialization strategy. Both quality and performance are improved. We defined a novel joint error to analyze the trade-off between quality and performance and determine the optimal number of iterations. We also have several things to try in the future. First, improving the initializing strategy to erase the artifacts Second, evaluating the curved or distorted surface. Third, analyzing the capability of additive light field factorization. Thank you for your interest. Now it's time for questions and answers.
Yeah, thank you very much for your presentation. So I again invite people to raise their hand or ask a question in the chat or the Q&A box. And while people are getting prepared, I'll start with a first question. So with this like vergence accommodation that you mentioned at the beginning of your presentation, with respect to additive light field displays, is like 2 layers something that is enough to help with the accommodation vergence problem?
Yes, there's previous work that do a user study to prove that 2 planes is enough for to improve the vergence accommodation concept. Yeah.
Okay, great. Okay, I'll go for, I don't see any raised hands or questions, so I'll go with another question of myself. So I'm wondering, so you have like this color initialization or depth aware initialization. Did you consider like taking into account temporal continuity for the initialization?
Not yet. Yeah. We have just do the experiment on static scene, but this will be a future consideration. Yeah.
I guess even for a static scene, if the viewpoint changes, you could still benefit a little bit from dynamic information on what to put on which layer, right?
Right. I agree.
So maybe more practical question. So you simulated a display, I think, at your result. Did you test your method on an actual physical device?
No, because just for now, I have no hardware to test. So we only do the test on by simulation.
Okay, I guess that kind of is problematic to do this like vergence accommodation testing just to see if your results are good.
Yeah.
Okay.
That's right.